So question 3 of the practice final gives us a solenoid of different materials. So part A through C all have some sort of solenoid made of different materials. We have a wire wrapping around this cylinder. That's what creates the solenoid, and the current flows in the positive dead-hat direction around this wire. So the current is flowing around, but gradually moving upwards. We define the positive dead-hat direction like so. In this question for parts A through C, we want to find the directions of our auxiliary magnetic field H, the magnetic field B, the magnetization M, the bound surface current KB, and the bound bulk current JB. We want to find the directions of all of these vectors for the different materials of the solenoid. In part A, we have a paramagnetic material. So of course, paramagnetic and diamagnetic materials have a magnetization that's sustained by some sort of field. And we can look in chapter 6.1 of Griffiths to read about magnetization, paramagnetic materials, diamagnetic materials, and ferromagnetic materials. But specifically for this paramagnetic material, so I'll write paramagnetic material, we have initially for the direction of the magnetic field B, we have some current flowing around the solenoid like so, and due to the right-hand rule, we curl our fingers in the direction of the current, and our magnetic field points in the direction of our thumb. So B, in this case, because of the right-hand rule, the B is in the positive z-hat direction. Similarly, because we have a linear paramagnetic material here, our auxiliary field H will be dependent on B like so with a factor of mu. When I look at this way, it's going to be 1 over mu. Either way, if we're looking at just the direction of the vectors, B hat will be pointing in the positive z-hat direction. So again, because we have that our current is flowing around, we, with the right-hand rule, curl our fingers in the direction of the current, and H hat will be in the positive z-hat direction as well. For the magnetization, we have a paramagnetic material, and in paramagnetic materials, we have that the magnetization M points with the magnetic field. So we have that M is parallel to B for paramagnets. And for a maybe more in-depth explanation of why this works for paramagnetic fields and not diamagnetic or ferromagnetic, you can look in your textbook. But essentially, for paramagnetic fields, we tend to have the magnetization of the magnetic dipole moments of each of the small moments within that material seem to line up with the magnetic field B, which means that we have M hat is positive Z hat with B. Our bound surface current, KB, has an enhanced field because it's paramagnetic. That's one of the definitions of a paramagnetic material, is we have an enhanced field because the magnetization points with the external field B, with the magnetic field B, not external. And we have that KB is given by the formula from our textbook, M cross N hat. Which in this case, if we have N hat will be flowing, N hat will be moving out radially if we're looking away from the solenoid. Our Z hat is pointing up. So this cross product where we have M in the Z hat direction, N hat in the S hat direction is going to be the direction of KB is phi hat. Because essentially we have the magnetic field is some constant, the magnetization is some constant C times our direction Z hat, that's what our M is, and our N hat is our direction vector coming away radially from our solenoid, moving like outwards like so. This is N hat is equal to S hat. And this cross product then gives us Z hat crossed with S hat, which is just phi hat. So our bound surface current will flow around the solenoid. And in the paramagnetic, the bound current is in the same direction as the free current. So that's something really important to remember. Here we have the free current I flowing around in the phi hat direction as well due to the right-hand rule. And how it's set up here in the solenoid, we flow it around the wire that's wrapped around that solenoid. So because it's a paramagnetic material, our bound current, as expected, is flowing in the phi hat direction, the same direction as I. Finally, we want to find the bound volume current density, which is just JB. And JB is equal to the curl of the magnetization M, which is just the curl of our magnetization, which is some constant times z hat, where again we know this is what m is given by. By doing this curl, we see that because this is a constant magnetization, this curl is just 0. So because the magnetization is constant, and we do the curl of that constant magnetization, this curl will always give us 0 bound current density. So JB has no direction because it's 0. So to summarize, for the paramagnetic material, we have the current flowing around the solenoid. Due to the right-hand rule, we can see the direction of B and of H. The magnetization for a paramagnetic material is always going to be with the magnetic field. So in this z-hat direction, in this case, our bound current surface density is given by our magnetization crossed with our direction vector n-hat, which is away from the solenoid in the s-hat direction. So we have z-hat crossed with n-hat, which just gives us phi-hat. And we know for a paramagnetic material, of course, the current will flow with the free current. So we should see that's in the phi-hat direction as we expect. And of course, the bulk current density in this case is 0 because the magnetization is just a constant. Part B of question 3 asks us to find the same as part A, except for a diamagnetic material. So diamagnetic material. I could have that spelled wrong from my notes, but we'll go with diamagnetic. Of course, again, for the magnetic field, the B direction, we simply look at the free current, we curl with our right-hand rule, and we say that the magnetic field points in the positive z-hat direction. Same as part A. Sorry, this is part B now. Forgot to erase that. This is part B, the diamagnetic material. So B hat is in the positive z-hat direction, as in part A. For the auxiliary field, exact same thing. Because we have a linear magnetic material, diamagnetic material, and we have the free current curling around, through the right-hand rule, H will also point in the positive z-hat direction. Now the magnetization in this case is the opposite of the paramagnetic case, where we have that the diamagnetic material has a magnetization that is opposite of the magnetic field. So for diamagnetic materials, our M is anti-parallel, so negative parallel, I'll draw the symbol here, to our magnetic field, which means that our M in this case will be negative z-hat. That's the difference between diamagnetic materials and paramagnetic materials, is that in paramagnets, the magnetization flows in this, or is in the same direction as the magnetic field, but in diamagnetic materials, it's in the opposite. This transfers through to our bound surface current because we have M cross n-hat again, where again, in this case, our n-hat is radial away, so s-hat direction, but in this case we have negative z-hat as our direction of our magnetization, so this will be in the negative phi-hat direction now, because we are essentially the exact same as in part A in terms of magnitude, but we're looking in the opposite direction because the magnetization is opposite. So this will be kb hat. And for the bulk current density, again, we have the curl of the magnetization, which again is just our constant. In this case, negative z-hat direction, but either way, this just gives 0. So there is no direction for our bulk current density. So again, just to summarize quickly, part B, for a diamagnetic material, our two magnetic fields, the auxiliary and the normal B field, will also be in the z-hat direction, just as we found in part A, because they only depend on the free current, and we have our right-hand rule with the current flowing around the solenoid, magnetic field points up. In the case of the magnetization, for a diamagnetic material, the magnetization is opposite to that of the magnetic field B, so we have that our direction vector is negative z-hat, anti-parallel to our magnetic field. The bulk current, the bound current surface density is just M cross n-hat, where n-hat in this case is the s-hat vector moving radially away from the center of the solenoid. In this case, this cross product again gives us phi-hat, but we have that negative sign in there from the z-hat, so we have negative phi-hat direction, which means that, I'm not sure if I can do this with my right hand, but we have our current, our free current flowing this way, and our bound surface current will be flowing the opposite direction. So I'll use my left hand in this case to be flowing like this. What that means is that this bound surface current will essentially be acting opposite to our free current. So we'll be kind of negating the effect of our current flowing around. So our free current I flows around up the solenoid in that direction, and our bound surface current will be opposing that, flowing in the opposite negative phi hat direction. And then finally, our bound bulk current density is 0 because the curl of the constant magnetization is just 0. So finally, part C of question 3 asks us to find the directions of HB, M, KB, and JB for a ferromagnetic material, kind of like a magnet. So when we again find our B and our H, which is going to be the exact same as part A and part B, where we have the free current I flowing around, right-hand rule, thumb points in the positive z hat direction, so B hat is positive z hat, and H hat is positive z hat. Exact same as part A and part B. For the magnetization, in this case for a ferromagnetic material, as you can see in question 1 of the practice final, the applied magnetic field, or the magnetic field, works to kind of align all of the domains within our ferromagnetic material, inducing a magnetization in the direction of that magnetic field. So again, we'll have our domains, and all of the magnetic dipole moments will be pointing in random directions, and when we apply, or we have that external magnetic field, or in this case the magnetic field due to the current flowing around the solenoid, when we have that magnetic field, excuse me, that will work to align all of the domains and will essentially shift all the dipole moments so that we have a net magnetization in the direction of the magnetic field. So M hat in the direction of the magnetic field Z hat. Our bulk bound surface density, our bound surface current density is again simply M crossed with N hat, which is again is going to be positive phi hat direction because of the exact same logic as part A, where we have the positive z hat direction cross product with the s hat unit vector n hat. That gives us the cross product of phi hat. And of course, again, we can see that the bound surface current density will be flowing in the direction of the free current, and essentially this ferromagnetic material will work to enforce that current. We're going to induce a bound surface current that's flowing with the free current, similar to the paramagnetic material case, due to the alignment of all those domains of the magnetization, and this current will be flowing with the free current in the phi hat direction, in the positive phi hat direction. And finally, again, we see that JB is just the curl of our magnetization, which is just 0 because it's a constant induced magnetization. There is no changing magnetic field. The magnetization within the material is staying the same. Therefore, we have 0 bulk volume current density, JB. Again, just to kind of summarize and wrap up question 3, for the ferromagnetic material, we have always that the magnetic field B and H, due to the right-hand rule of the free current, will be pointing in the positive z hat direction as we wrap our fingers with the current. The magnetization for a ferromagnetic material will be such that it's aligned with the magnetic field because all of those domains of the magnetic dipole moments will sort of align with the field, not necessarily completely, as they all have some sort of interaction with their neighbors, but the net magnetization will be in the direction of that magnetic field. The bound surface current is just given by the cross product, as we saw in part A and part B, positive phi hat for this case, and the JB is again 0 because of the constant magnetization. And that is the sum of question 3. So for the para, the dia, and the ferromagnetic materials, what we need to remember is for the paramagnetic material, we have the magnetization is with the field. For the diamagnetic material, the magnetization is anti-parallel or against the magnetic field B, so it's always in the opposite direction. And finally, for the ferromagnetic material, all of our domains will sort of shift and align so that we are not necessarily all exactly with the magnetic field, but the net magnetization is in the direction of the magnetic field.